Actually, I'm asked to deliver the first talk on the introduction to Verilog HDL, but I'm not going to teach you a language because nobody can teach, in my opinion, uh, anybody a language. I can't go through the syntax. We will learn Verilog through examples. That's what my strong belief is. So, what I'll do is I'll tell you about the background stuff, and once the background is over, I'll talk about. Uh, I'll just take up an example after giving you a broad structure of Verilog, and then we'll start learning Verilog through an example, because that will help you in understanding how you can use this language to design useful systems. So this is the outline. I have not given you the full outline. It's just a very partial outline. First of all, I'll give you the background, as I told you. Then, what is the motivation? Why at all we need a hardware description language? Can't we survive without a hardware description language? And then, of course, there are multiple possibilities why I have taken Verilog HDL. Why not some other language? Why not C? Why not C++? What is the problem? And then, of course, the real topic. I'll introduce Verilog and with the help of examples. Before starting this slide, remember HDL is for designing digital systems. It is not for designing digital circuits. It is not for designing analog circuits. You have a separate subset of Verilog and other HDL which is targeted for circuit design. We have Verilog A and we have other options as well which can be used for designing circuits, digital circuits as well as analog circuits. This Verilog, which I'm going to cover today, is for designing digital systems. Systems means when I have very large number of transistors, maybe billion transistors, very complex circuits. How those circuits can be designed, I'll call that as digital systems, which are very difficult to design at the circuit level. At the circuit level, the problem is defined in terms of the interconnection of transistors. But in a digital system, I will never define this problem as an interconnection of transistors. I'll follow a different approach because if I define such a big problem as interconnection of transistor, it will take years to carry out simulation. So it's absolutely impractical to design big complex systems at the transistor level. So nobody uses these languages to design big circuits at the transistor level. You basically describe systems. So that should be very clear. What is the driver for it? Now I'll throw a problem. Problem is, let's say I want to. Everybody knows FFT processor, FIR filter. These are nothing but algorithms. These are algorithms. Now, this algorithm I can realize in different ways. What are the options in the table? The options are, I can realize it using an embedded microprocessor, like an ARM, or I can realize it using a general purpose Intel processors. What I have to do? I can use MATLAB, I can use C or C++, any language I can do for coding. That is the usual practice. That is one option. The third option, which is a slightly better option, if the algorithms are in the DSP domain, I can very well use a DSP processor rather than an embedded processor or a general purpose processor. This DSP processor, since it is tailored to implement MAC operations very fast, the throughput which I'll get through this processor will be much better compared to an embedded processor or a general purpose processor. This is the second option. Now I have a third option. The third option is I can use configurable logic, reconfigurable logic, maybe field programmable gate array to realize the same algorithm, FFT process. The algorithm is the same. The ways I can implement it is different. So these two are purely software solutions where I'm writing a code and implementing it on an embedded processor machine or on a general purpose machine or let's say on a DSP processor machine. But you have another option. If you're not able to meet the speed requirement, the throughput requirement through these channels or they're highly energy inefficient, then there's another option. Why can't you make a hardware dedicated for the algorithm that you want to implement? And that leads you to this option. This is your configurable, which is your one option. This is the field programmable gate array. So why don't you create an architecture for a given algorithm? That's the third option. Another option, which is much more energy efficient, is your hardwired custom. We call it application specific ICs, where I'm not using any, I'm basically creating a chip for an FFT processor dedicated for that particular application. So this is the most energy efficient, but it is least flexible. I can't change it. FPGA is much, because I can change the field programmable gate array the way I can change software. Second option. Then of course these are the two options which are very energy inefficient. Gives you lower throughput. So if you're not able to meet the throughput requirement using these options, then you have an FPGA option, or even better, but the flexibility goes down from right to left, but the energy efficiency goes up as I move from fully flexible to standard cell ASIC approach where you can't change things. Let's say I want to update my FFT because of my new requirement. It's much harder to do it here. It's much easier to do it there because just you have to change the code there. And here it's a bit difficult. FPGA, of course, you can do it, but of course not like this ASIC, application specific. So this whole course, I'll talk about the whole workshop, is about how you can design an FFT processor, which is an algorithm, in a field programmable gate array. One option, the same thing you can do it in applications. So how to create an architecture for a given algorithm. Is the relevance clear? So this course, you'll learn about the whole workshop. I'm just a starting point. How to create architectures for a given algorithm. And of course, in this, I'll let you know how the FPGA fits into the whole story of creating an architecture. That's the next slide. Any questions? It will be highly interactive. You can interrupt me anytime, and I'm more pleased to answer it. Right? So it's not like a broadcast mode. I am rather interactive. I told you already. This is under these two categories. This or that. This is you are writing basically. You're using a PC or an embedded microprocessor to using MATLAB or C here as well as there. Or maybe here you might be using assembly also. It depends on the application. Now, this is the problem. This is a general problem, because the general problem is ultimately for any design you have to meet a specification. For all the DSP stuff, let's say FFT, data is coming at some sampling rate. You have to process that information at the same sampling rate. If you do it at a lower rate, of course, there will be data logging up and the whole thing will be destroyed. You have to process at a faster rate compared to the sampling. And you can't gain much if you process at a much higher rate, because then the power goes up. So just you have to process at the required sampling rate. So one sampling rate is your specification, that is your speed. What is speed required? You have to operate the architecture using batteries. So again, the power plays a very important role. Then you have to accommodate this architecture in the minimum possible area. So the area also plays an important role, because the area decides the cost. Silicon space is very, very expensive. Then you don't have years to design it. You have to design it in the shortest possible time, because you must be ahead of competition. And therefore, the design time is very important. And the last looks trivial, but it's important. You must see to it that whatever you are designing, you must be able to test it without any issues. So that's a very, very important requirement. You must be able to quickly test whether your chip is working. So if you put something into it to make the chip testable. So these are the broad specifications. The three most important ones are the speed requirement, that's the frequency of operation, the power dissipation, and of course the area, because the area decides the cost. And cost, of course, is a very, very important driver. So this is the typical design problem, and then you have to design it keeping all these things in mind, using whatever channels you have for carrying out the design. Now, this is a very important chart because this will help you to relate an HDL with what you already know, circuit level stuff, SPICE. Now, when you use SPICE to create your design, analog circuit or digital circuit, you are basically operating at the circuit level. So whenever I have a circuit level simulation, it primarily boils down to using SPICE or some other circuit simulator to do the job. It can be a digital circuit, it can be an analog circuit where you define a problem as an interconnection of transistors. So that is very, very important. In this course, we will not talk about circuit simulation. We will move the problem at a level where the problem is less complex. The problem is most complex at the circuit level because you are defining a problem as an interconnection of transistors, and there are billions of transistors in digital systems. You cannot handle that complexity at the transistor level. So you have to somehow reduce the complexity level by moving from a lower level to a higher level. So let's move from circuit level to the gate level. At the circuit level, you must remember, if you recall, you have to solve linear equations, differential equations, all sort of equations. That takes a lot of simulation time. So this takes a very long time. I cannot use this mechanism to design a billion transistor circuit. I must have a faster simulation mechanism. So rather than using differential equations or rather than using exact voltages and currents, why not? Because in digital, I'm really bothered about 0, 1, X and Z. I'm not bothered about the exact voltages or current if my circuit is working. So the industry moved from the circuit level to the gate level, especially for creating digital systems. So in the early 80s, all the microprocessors, they were designed at the gate level. Some critical portion of the circuit level, most of the portion of the gate level, where basically if I say a NAND gate, I will not define a NAND gate as an interconnection of transistors. I will define a NAND gate with a delay, with a power dissipation, and with this truth table. So I'll apply zeros and ones and verify its functionality rather than bothering about the actual voltages and current, which takes a very long time to simulate. And therefore, the simulation level for digital system went up from circuit level to the gate level. But I cannot simulate at the gate level unless somebody else might have done the design for me at the circuit level. So let's say I have an AND gate which I want to use it at the gate level in my circuit, in my system. So I must know what is its power dissipation, what is its delay, in all setup time, hold time, all the important characteristics of a gate. And those characteristics will be extracted by somebody else at this circuit level. And this led to what is the concept of library-based design. So I have a library of components. I can pick components from the library and use it in my design, only those components which are available in the library. And that led to the concept of what is called gate level design. So all microprocessors in the early 80s, they were designed at the gate level because simulation time which it takes at the gate level is much shorter compared to the circuit level. And then as the complexity picked up, people realized, okay, even gate level design is not working. Why? Because from day one, your gate level design is technology dependent. You know that I have to, once I start designing, I have to fabricate my design in this foundry, in this particular foundry I want to fabricate it. I don't have an option to change because from day one I am picking components from the library which is supplied by the fabrication house where I want to fabricate this circuit from day one. It's technology dependent. So the fabrication house knows that after 2 years of hard work, they can't go anywhere. They are dependent on us because all the designs are based on our technology. So now they're open to blackmail, all sort of things happen. So the industry, the designer realized, let us do something to make the design technology independent rather than technology dependent. So that gave rise to this research in the domain of what's called hardware description languages. Why not describe designs not as an interconnection of gates, not an interconnection of multiplexers, encoders, decoders, digital systems, but with the help of a language, just capture their behavior, and there must be some automated tool that converts this hardware description into a gate level net list, which we were already doing manually using handcrafted, which is very painful for complex circuits. So that led to the idea of moving over from gate level design to what we call it high level design or HDL based design, where we capture the behavior of the design and not the actual interconnectivity. Is the concept clear? So why the HDL came into being? What was the motivation for moving from the gate level, which was the traditional level at that point of time, to a level where the design becomes technology independent? And of course, it's much easier to write a code compared to carrying out the interconnection. You can handle complexity in a much more effective way. Now, this gives you a problem, very simple problem I highlight. You just add 16 numbers, carry out the summation. For this simple problem, there are multiple architectures. How can I add it? If I have one adder, then I have to do iteration 16 times to carry out the summation. If I have two adders, if I have only a full adder tree, I can do it in one time domain. So simple problem can give rise to a multiple architectures, and once these multiple architectures are ready, I can code it. I'll talk about it, where I have a memory to store the information, and then of course the adder block, and I have only one. This is an adder tree shown as just one adder where I'm adding 16 numbers at the same time. So I can have the same problem I can describe in more detail at a level which I call it register transfer level. I'll talk about it in more detail in a short while from now, or maybe in my next lecture tomorrow. But so this is the most important level where all the designs are captured today, where any digital system, I can define just only two things. Either you store information in memory, you store information in registers, you store information at the input port, which is also a register, an input register, an output register. So what happens in any digital system? You either transfer information from register to memory, or from memory to register, or from one memory block to the other memory block. So this is called movement of information from one register to another register. Memory is also an area of register. So this is movement. The second thing which happens in any digital system is transformation. Data transformation. Where does it happen? Where does it happen, data transformation? In which block it happens? What is the most important block where the data transformation takes place? You transform the data. From some input data, you create a new data. Where does it happen? Yes? ALU. So ALU is the processor block where it happens. So what is happening in any digital system? You either transfer between registers, or you transform the data in the ALU or the arithmetic logic unit, and now this transformed data must be stored in some register. So any digital system can be defined in terms of only two things: register transfer and register transformation. If you're handling this problem in this way, you are basically addressing or attacking the digital system design at the RTL level, the register transfer level. This is and most of the HDL code is written at this level, where the problem is defined in terms of only register transfer and register transformation, not in the form of some circuit, not in the form of some flip-flops, not in the form of some basic state diagrams. Those things can handle at the much lower size problem. For complex problem, this is a standard way. And remember, the last thing shows you, even it's not visible. It is just showing you a way out. The past, in the 80s, all the microprocessors, they were designed at this level. And look at the interconnection patterns. Hundreds of thousands of gates, they were connected like this. This is your gate level. For the same design, this is the gate level that you get. So what we will do in this course is, we should learn how I can capture the behavior of the design at the register transfer level. Some automated tool, we call it synthesis tool, will convert this description, which is your hardware description, HDL description, into a gate level netlist automatically. And this process is almost error-free if you are able to write a good synthesizable. I am using the word synthesis. Writing an HDL code is not difficult. It's easier. But writing a synthesizable code is much more difficult than writing an HDL code. The two things are quite different. So look at this. This was the process earlier on. But now you capture the behavior at the RTL level here. And this is an automatic channel which call it logic synthesis, which will automatically give you this huge gate level netlist. So the design moved from the very complex gate level to a much lesser complex register transfer level, where the problem is described not in terms of technology, but in terms of a language. We call it a hardware description language. Is the basic thing clear? So this is the background, because this background is important. Otherwise, I can't teach you Verilog straight away without knowing where it is used, why at all we are doing it. The motivation is most important in the background. So this will set a stage for our next set of slides, which is design domains, I call it. So now, the most important domain for me is, I'll capture the design's behavior. For this course, it's most important you should know how to capture our digital system in terms of behavior. We earlier used to do structural by defining a digital system problem as an interconnection of blocks. We'll not do it. We'll capture a problem in terms of its behavior. So the design it has different flavor. The first and the most important flavor for you is your behavior block. The design, you should know how to create the design at the behavior level. This workshop is all about how you can create a design at the behavior level. Then, as you must be knowing by now, that the next detailed level is the structural level, which is nothing but the interconnection of sub-blocks, basic blocks. This structural level will be automatically created from the behavioral level by using, we call it a synthesis tool. We call this mechanism as logic synthesis, where a behavioral description is converted into a structural description. Structural means interconnection of blocks, gate level, automatically, without any human intervention. And this is an almost error-free process if you know how to write a good quality synthesizable code. Then, once the structural level is clear, you see the design is still not over, and I think you have a relevant background. Layout is the most important thing. Ultimately, you have to send the layout if you're doing ASIC design. If you're doing FPGA, it's implementation. So ultimately, you have to, for ASIC, you have to prepare a layout, because the layout is given to the foundry for fabrication. So the next level is, we call it a physical level. This is a third view of the same design. A design has three views. Behavioral view, which is RTL in terms of HDL. Second is structural, gate level. That can also be in some HDL, but this is interconnection of blocks, not behavior. And then the third view is the physical view, the layout, how the layout will look like. So the whole digital system design problem boils down to three steps. First, create a behavioral view by capturing the RTL description in an HDL, maybe Verilog. But while creating the view, you must be clear that this view should not have any error. You have to verify the functionality of this view. So first create the view and then verify its functionality, behavior. Then logic synthesis will help you in converting this behavioral view into a structural view. Again, this structural view must be verified through simulation. the functionality at the behavior. Whether whatever you have done to the behavior is the structural view the same as the behavioral view. You have to set up an equivalence. Only then synthesis process has not introduced any errors. Otherwise, synthesis process must have introduced errors if the two views are not equivalent. For the same input, you should get the same output. Only then the behavioral view is the same as the structural view. Once you have set up an equivalence of the behavioral view and the structural view, you move on to the other last view that's called the physical view. So once the physical view is ready, again, you have to extract all the parasitics from the physical view, and based on that parasitic, again, you have to carry out verification. This physical view should also be equivalent to the structural view as well as the behavioral view. When all the three views are equivalent, you have proven it, the design is ready for fabrication. This is it. This is the full story about digital system design. And what your story ends here is, I'm not talking about ASIC for this course, but for ASIC, for FPGA it will be slightly different. Physical view will be implementation rather than layout. So you can have that idea. But mainly this workshop, you should learn how to create behavioral view. That's the most important view. HDL is famous for creating a behavioral view. It is not famous, it is not useful for creating a structural view, although it can do it. It's not meant to do it. You have to create a most compact view because the design is huge. And the most compact view is the behavioral view. It's not. The structural view is much more complex than the behavioral view. Physical view is even more complex than the structural. So the information goes on, amount of information goes on increasing as one moves from the behavioral view to the structure. Is that clear? Any questions? Let's move on. Now this I have already told you, the behavioral view, you capture the design, then you do logic synthesis, you come to the gate level view. Before that, you have to carry out the verification, we call it simulation. And then the physical view is your layout. And then you have to carry out the post-layout simulation before submitting your design for fabrication. That makes sense? Shall I move ahead? Now, this sets the stage why at all we need HDL. We need HDL to describe behavior and not implementation. This is for behavior. And remember, behavior is something which is independent of technology. Very, very important. Behavior doesn't depend on technology. Just like it's also called high-level design. Just like language C or C++, it is system independent. You can use it on laptop, you can use it on a Sun, the same sort of code works. Just the same thing you can extend to an HDL. HDL design is, here if you don't have system, it's technology independent. Just, it's also called high-level design because all high-level languages of computers, they're also platform independent. Make model independent of technology, that I already told you, is speed up simulation of large systems. Why? Because now you can handle complexity. The HDL coding is very compact. That design at the gate level, you can yourself gauge, it's too complex. It's too complex for a billion transistor circuit. High-level design is carried out at a level higher than the gate level. We are not doing anything designing at the gate level. We are designing at the behavioral level, which is higher than the gate level. We call it the RTL level. So this I'll skip. I'll move on. I think this is a bit of history you must be knowing. But before starting this, there are two very important languages, competing languages. One is Verilog, another is VHDL. VHDL stands for Very High Speed Hardware Description Language. Verilog I have taken deliberately in the department. I popularized it because I know also VHDL, because it's very similar to C. VHDL is similar to ADA, which is a very complex language, and therefore it's much harder to learn compared to Verilog. And then because Verilog is very natural, it's It's derived from C. So what are the syntax in C? The same is almost extended to. It's much easier to learn. Now, this is for digital system. You have Verilog A, Verilog for analog, which you can use for designing digital circuits or analog circuits. Similarly, you have VHDL AMS for designing analog circuit as well as digital circuits. So this Verilog was developed in 1984-85 at Gateway Design Automation, and then it's now an IEEE standard. So it's a standard language. Anybody can use this standard language. So any vendor can come up its own simulator, its own synthesis tool, because Verilog now is a IEEE standard. It's not an in-house language, it's an open language. So now let us start with because I think there are people from white background, so let's start learning Verilog through examples. And I'll start with the simplest possible example. Some of you might be knowing it as well. But I always start with this very simple examples to learn Verilog. So, in a Verilog, everything is a basic building block is a module. A system is a big module. Within the system, you have two sub-modules, Comp1 and Comp2. And within Comp2, you have another module inside Comp2. So, basically, everything is a module. Some are bigger modules, some are smaller modules. Everything in a Verilog is a module. Module is a basic building block of Verilog. Now, so you have a module, and then the different modules communicate with each other through what's called ports. You have an input port, you have an output port, and you also have a bidirectional port. So this is how the modules communicate. So this is input A is this an input port, B is an output port, and then I have a port C, which is a bidirectional. So this is how a module look like. You have a module, then the name of the module, and right on some of the final points that are very, very important. In Verilog, the traditional thing is, although I have not followed it, first you have to put the outputs, and then you have to put the inputs. And then, of course, you have input A, output B, and you have an out C. And then every module must end in an end module. In an end module, there is no semicolon. Remember, it's very, very important. In the end module, you don't really have a semicolon. Every statement must end in a semicolon, including the module. Now, you have some signals which are neither input nor output, and they must be declared as type wire. So it's very, very important that some of the intermediate signals, all the intermediate signals must be declared as type wire. Now, the most important thing, whatever statements you put inside this module, they are not sequential statements like a normal high-level language. They are concurrent statements. So I again reiterate, never ever try to put inside a module statements which are sequential, like if-else, like case, like while, like for. All these are traditional high-level language constructs. They cannot go directly inside a module. They're not allowed to be put directly inside a module, because whatever is allowed inside a module, all these statements inside a module, they are concurrent statements, because this is a language meant for describing a hardware. And you know, the hardware is not sequential, it is concurrent. Otherwise, there is no need of a spatial HDL. I could have used C for describing the hardware. The greatest stumbling block was all the traditional high-level languages, they are sequential in nature. But this spatial language is primarily used to describe hardware. And therefore, it should also behave like hardware. And now what is the hardware behavior? It's not a sequential behavior, it's a concurrent behavior. And therefore, whatever you put inside the module directly must be concurrent. Means the position of this statement is not important. All these statements will appear to execute concurrently. The simulator will ensure that all these statements which you put inside a module, directly inside the module, they appear to execute concurrently. Otherwise, mimicking the hardware behavior is impossible. Because in hardware, if I have 10 NAND gates, if the input changes to 10 NAND gates, all the outputs will change after some delay. Or let's say if the delay is 0, all the outputs will change the same time. How do you mimic that behavior in software? Because here I am using software to mimic the hardware behavior. And therefore, it's very, very important that whatever you put directly inside the module, all these statements must be concurrent. They are not sequential. So, Verilog can describe a module at the behavioral level. It can also describe a module in a level which will be clear very shortly. We call it a data flow level. And then a gate level, which is nothing but a structural level. The structural means where you define a complex problem as a set of interconnection of smaller sub-blocks. So you can describe this, you can capture the design at this level, you can capture it at this level, and these are the 3 levels. Now what I'll do, I'll take an example and show you how the same code can be written at different levels, like behavior, like data flow, and the gate level. So this is how a module goes. You have a module, I told you already, and then end module. Then what must be there inside the module? What are the different concurrent statements that you can have inside a module? So what are the options? The options are, you can construct a module by combining basic modules. So you can have instances of smaller modules called inside a bigger module. That's one option. We call it structural description. It's structural modeling with Verilog. Or you can use some of the data flow statements. All the data flow statements, as will be clear very shortly, they're also concurrent statements. If there are 10 statements of data flow, all these 10 statements will appear to execute concurrently. They'll not execute sequentially. And then the most important description, we call it a behavioral description. And that is the most important thing that you want to learn. That is with the help of always and initial blocks. So what my stress will be, you must know how to use the always block primarily. And of course, initial blocks in the test benches to create digital system, to capture the behavior of digital systems. That is the most important aspect. So now you have 3 descriptions. Either you use always, or you use data flow, or you use structural, where you construct a bigger system by combining smaller systems. Or you can use a mix of behavioral and data flow in your design. And then synthesis tool will help you create the full structural level of design. Make sense? Now let us start with a very simple example, just to give you a flavor, because I was told that there is a mixed audience, so I started from a very, very basic. So the problem is very, very simple, and you know most of the problems here. The problem is XNOR gate. So what I'll do is, this basically captures the behavior. This is the behavior level description of an XNOR gate. So I'll go through it and I'll explain each minor steps, because minor steps are very, very important. Some of the students, they miss the minor steps, and that's why there's so many errors. Module, then the name of the module, and within brackets, first the output followed by the input, and then you have a semicolon. Then you have to define the inputs and outputs, and then end module. This will be common to all the description of the same module. Whether it's data flow, whether it is structural, this portion will be common. This end module doesn't have a semicolon, remember. You have module and then you declare the inputs and outputs. Now in the behavioral description, you also have to do one thing extra. Remember, one thing extra, I'm stressing it. What is that extra thing? The output must also be declared as type register. Remember, this declaration. You have to do only in the behavioral description. This you don't have to do in the data flow description or in the structural description. This has to be done only and only in the behavioral description. Now, this is a very, very important way. You must be wondering from where the always statement comes in. How the always statement helps in modeling a hardware. Remember, always statement I'm putting directly inside a module. So it cannot be a sequential construct. It is a concurrent construct. If there are two always statements inside a module, both the always statement will appear to execute concurrently. If there are 10 always statements inside a module, all the 10 always statements will be concurrently executed, will appear to execute concurrently. The position of the always statement is not important, whether you put it first or you put it last. That is what is meant by concurrent design. Always statement is a concurrent statement. Initial statement is also a concurrent statement. And these statements therefore can be put inside a module. This is very, very important and must be borne in mind. Now, it's let us okay. I'll not use the pen today. Okay, let us have this. Let's say this is a gate. This is an AND gate. Let's have an AND gate. The AND gate output will change only when either input A changes or input B changes. So there are two options for the output to change. Whether the output of the AND gate will change if there occurs a change in the input A or the change occurs in the input B. That is, the AND gate should be sensitive to changes in the input A or changes in the input B. So that is the very important essence of an always statement. That is, the output of the gate will change whenever there occurs a change in input A or whenever there occurs a change in input B. Otherwise, the old value will be retained. Otherwise, the old output will be retained. That's the behavior. So the old output will be retained. The output will change only when there occurs a change in either A or B. Otherwise, the output will not change. Now let us see how the always statement helps in modeling this behavior. It's very easy to learn Verilog because only the always statement is the statement to learn to capture the behavior. As simple as that. You don't even need to learn initial, only the always statement. How does it work? And you have to do it for an infinite time. This will go on and on and on and on. This you just wait for an event on signal A or signal B and accordingly adjust the output. So what happens? You always, this sign at the rate is nothing but a sign of an event. Event means event switching either from 0 to 1 or from 1 to 0. This, what does it mean? Always. What do you do? What the always statement should do? Always. Always what it should do? Wait for an event on what? On signal A or on B. Because these two are part of the sensitivity list. If by mistake I'll put that this always statement is sensitive to signal A, it means this piece of code will not be executed if there occurs a change in signal B. So note down one very important thing. In a combinational circuit, I repeat, in a combinational circuit, all inputs must be included in the sensitivity list. It's a very important statement. All the inputs must be included in the sensitivity list. In the sensitivity list. Otherwise, the synthesis tool will give you errors and you will get even erroneous output in the simulation. You get my point? Why I'm saying this code will not be executed if, let's say, B is omitted, because this code is no longer sensitive to changes in B. Is it clear? So it's very, very important to include all. Then you always have a begin and an end. This is the begin of the always statement, and this is the end of the always. This should be demarcated where the always statement starts. It's a compound statement, so you have to put a large number. Now, the most important thing, all the sequential constructs, because normally you describe behavior using sequential constructs of a high level language. They are allowed only at two places. They are allowed only inside an always block, or you can they are allowed only inside an initial block. You cannot write those if statements inside a module directly, because they are not concurrent constructs, they are sequential constructs. And all sequential constructs are allowed only inside an always statement or inside an initial statement. They are not allowed outside the always statement or outside the initial statement. It's very, very important. Is the point clear? So what happens? How the always statement will execute? Always. Always means it's an infinite loop. It's an infinite loop. Always, what do? Wait for an event on signal A or B. As soon as an event takes place, execute this piece of code, and then again go back, wait for another event. And this goes on and on and on and on. This is how it happens in hardware. Do you agree? Therefore, always statement is there to mimic the hardware behavior. That's simple. It is designed to mimic the hardware behavior. And if you have a one-to-one correspondence with VHDL, in VHDL you have a process statement which does the same job as an always statement. So if you know one language, you can switch over to the other without any problem. So what happens here? Now, this is for XNOR gate. So what is the behavior of XNOR gate? If the inputs are identical, the output is 1, else the output is. Is this clear? So what happens if A equals B? That is, you compare A with B. If the two are equal, then the output will be assigned 1. That is, this is your procedural assignment. This assignment is inside. These are called procedures, always and initial. So because there are assignment outside these procedures also. So we call this procedural assignments. So if the A and B are equal, then the output is assigned 1, else the output is assigned. It is so simple. So you capture the behavior. Now look, there's no technology coming into this code. It's technology. That's the beauty. Now I'll move on to the next piece of code. This is the same code, same problem, but Verilog, for the same module, for the same block, you can write different codes. And all are functionally equivalent. This is the data flow model for the same XNOR gate. How does it work? Again, look, the definition remains the same. The only thing is, okay, one thing I left. Remember, this thing is very important. The outputs, the output out must be, the output out is receiving values, which must be retained between events. Therefore, the output must also be declared as type register. Remember this forever. The output must be declared, all output must be declared as type register inside the always statement as well as inside the initial statement. Now let us get down to what is called the data flow constructs. Now in the data flow construct, remember the data flow is defined by the assigned statement. Only one statement assigned. This we call it continuous assignment. And if there are 10 assigned statements inside a module, all the 10 assigned statements will appear to execute concurrently. Now, what it does, the output out, it's nothing but the same AB plus, this is AND operation, this operation is OR, this is your complement. So this equation is nothing but the output A will be AB plus A bar, B bar. So the right hand side will, as soon as anything changes on the right hand side, this will be executed and then it will be assigned to the left hand side then and there. In this case, no delay value is assigned. It is zero delay simulation, idealistic. You can also introduce delays also to make it more realistic, because otherwise it will be zero delay simulation. So you can do that. Here also you can put some delay. Here it's ideal zero delay. It doesn't work. When you synthesize, the result will be different, because after synthesis, whatever circuit you get will be in some technology. It cannot have zero delay. So in order to match the results which you are getting after synthesis to what were you getting before synthesis, it is very important to introduce at least some delay, unit delays, if not some big values here, so that the behavior before synthesis should match the behavior after synthesis. Because in this case, it appears to be just the zero delay simulation. This is very, very important and must be borne in mind. Is this clear? So if there are 10 assigns, all the 10 assigns will appear to execute concurrently. Data flow construct is primarily used for describing some combinational circuits in a very effective, simple combinational circuits in a very effective fashion. So at the RTL, you can use some small amount of data flow with the always statement. That combination really works at the RTL level. Now, this is the last model, structural, where the XNOR gate now is defined as a collection of basic gates already known to Verilog, like OR gate, like AND gate, like XNOR gate. In this case, we are not using XNOR gate, AND gate, OR gate, and OR invert. So, this is your structural model. Normally, this model is the output of the synthesis tool. But here I am just giving you an idea that even Verilog can be used. There also Verilog output is there to model the same design at the structural level. But what you need to know is how to create the design at the behavior level. That is what you have to do. You have to learn. That is most important. So in this case, one thing which is different is this is the same. One thing is different. All the intermediate signals must be declared as type wire. Must be declared as type. So you have intermediate signals bar A, bar B, X and Y. They must be declared as type wire. Now, in order to construct, you know the basic connectivity. Basically, first of all, we generate bar A and bar B, and then we need an AND gate, bar A, bar B, and then this will give you AB, and then you OR it. So it will be AB plus A bar, B bar. So you can construct a structural flow by the combination of two NOT gates, two AND gates, and one OR gate. Remember, this is a standard NOT gate available, known to Verilog. But in this design, I am calling that as N1. And therefore, it is NOT gate is a standard gate available in Verilog, or a standard model which I have created somewhere else, if I want to call that. And then N1 is the name of that module here, N1, because I am calling it twice. One with N1 name, another with N2. And first I'll put the output and then the input. So first is the output bar A and then the input A. The output is bar A and the input A. This convention is very important. First the output and then the inputs. Then another NOT. AND gate, of course, the output is X and the inputs are A and B. And then another AND gate is A2 and the last gate is OR. That makes sense? It is self-explanatory. I don't want to devote time on this. So this is the structural view of the same design. The second was the data flow view of the same design. The first is the most important, behavioral view of the same design. Normally we create the behavioral and the data flow views, combination in general with HDL. And then this view will be automatically generated from those views by the synthesis tool. Now this is the most important thing. We have created the design in Verilog. Now we should know how to test the design. Remember, this is not a trivial task. Testing or verification takes longer time than design creation. The number of code lines written for testing is much more than the number of lines written for design creation. So it's not a trivial task, it's a tougher task. And therefore, verification engineers are in great demand in the industry. So what happens here? It's like a black hole. Nothing goes out, nothing goes in a test bench. So you have a module with no sensitive release. Module, you can put any name and then a semicolon. And then I have an end module just like this. So it's like an old fort where everything is inside. Nothing goes out. All the population is also inside the fort in big forts. So it's like a self-contained world. So you have a test bench here. And then, now there are three different important portions of a test bench. Three different important portions. I can reiterate. First of all, test bench means I want to test the block which I have created. So just go to the electronics lab for some time, virtually, and then think of a situation, what I need. So first of all, I need a breadboard with a design I want to test. And then I need a signal generator to apply the inputs. And then I must have something to record the CRO, to record the output. So three things I need. A signal generator, of course battery will be there, let's say. And then you have a design breadboard at which I put my ICs and then I apply the inputs and get the outputs. So let's identify those portions. First of all, I have created three designs. I'm now picking up one, any one, right? So XN is the design I've created. By the way, I can call all of them by put different names and then I can check all the three should give you the same output, only then the three are equivalent. I can do that also. But then I have to give three different names and call all those threes. But unfortunately, I have put the same name XN here. So let's live with that. Now, forget about this for the time being. Let us start with this one first. XN top out A comma B. What does it mean? XN is the name of the module which I want to test. And top is the name of the same module under here. The stimulus knows only top. It doesn't know XN. XN you have to give the link also. Only then it will go. Or maybe XN is somewhere down. The same file. Right? So, and then output and followed by the inputs. That makes sense? So now you have called the design and the test in the stimulus. Now it's a part of the stimulus. You have called that design. Make sense? Second portion. There must be a mechanism to apply the inputs. Different combination of inputs to the design and the test. And since I am using an initial statement, all the left hand side variables must be declared as type. Which type? Registers. And therefore, in this statement, I have to apply which inputs? A and B must be applied to the design and test. A and B are the two inputs. So, they must be declared as type. Now, I have to take the wire output from my breadboard and connect it to the CRO. So, the output must be declared as type. Because it's a wire. Now, look at this. This is very, very important. Write down this. This is a very important term. Initial block. I am putting it directly inside the module. It's a concurrent construct. It's not a sequential construct. Just like always state. But always means infinite. Initial means the only difference is it executes only once. I can retrace. That's the only difference. Now what happens here? Initial, start, begin and end here. Look at this. Now I'll start with A is equal to 0, B is equal to 0. First value, I have to verify the truth table, 0, 0, 0, 1, 1, 0, 1, 1. Now the problem is, all the verification process starts at time t is equal to 0. So there must be some mechanism to advance the simulation time. So for that to happen, I have one option, this is hash. Hash 10 means, there's no units here, I have to define the units, I'll tell you how to define the units. Hash 10 means, you advance the simulation by 10 hypothetical units. It's not the same time. So this value is valid from time t is equal to 0 from up to time t is equal to 10. At 10, the value changes. A remains 0, B becomes 1. Alright? So I can draw the waveforms also. From time t is equal to 0 to t is equal to 10, A is equal to 0, B is equal to 0. From 10 to 20, A is 0, B is 1. From 20 to 30, A is 1, B is 0, and so on. And up to 40, I have A is equal to 1 and B is equal to 1. So for every 10 time units, I have one combination which is valid. 0, 0 from 0 to 10, then 10 to 20, another 20 to 30, and 30 to 40. Dollar finish is a system command. Dollar finish means you terminate the simulation. Apply all input combinations and then terminate the simulation. And this statement will execute only once. That's why I've used initial statement. Write it down. Initial statements, I'm again reiterating and remember this forever, initial statements are used only in the test benches. I again reiterate, in some of the books it's wrongly written, initial statements should not be used in the design modules. Initial statements should never be used, I would say, should never be used in the design modules. They should only be used in the test benches. Otherwise, there will be problem with the synthesis tool. It looks fine. Simulation might give you good results. But initial statement used in the design module will give you some errors during synthesis. Never ever use. There's no need to use initialization. You can always do using reset. There is no need to use initial statements inside a design module. Only always statement must be used inside a design module. Initial statements are used only in the test benches. So this is very important. This is like your signal generator. This is your signal generator part. This is the module called. These are the declarations that you have to do. What else? CRO again. What is left? My CRO. So I have another initial statement for the CRO. Since there is one statement, I don't need begin and end. But I think it's better to use begin and end as a habit. So what happened initial? What it does mean $monitor. $monitor again is a system command that you have to learn. $monitor, $display, so many commands are there. File display that you have to learn with. $monitor means whenever any signal, which are three signals, out A and B, whenever any of these signals changes, it displays the result. So what happens? It also $time, it also displays the simulation time at which that change has happened. So what it does, it displays the time, it displays the output and the output and A and B. It's just like C. Look at the constructs. Output and then of course percentage B means binary. You display in binary what? You display output. You display A and you display B. Any questions till now? Anybody? Test bench? Is the test bench clear? So writing a test bench is very, very important. Don't assume it to be trivial. It's even more difficult than creating a code. Although for this problem, and remember, HDL is not designed to describe an XOR gate. Neither basic blocks. It is for converting algorithms into architectures. If you don't know how to do that, you don't know real HDL usage. Any algorithm in this world, you should be able to design its architecture. Remember, another very important point. Coding is very simple. Verilog coding or VHDL coding is very simple. What you should learn is creating an architecture. It's just like algorithm creation is very difficult, but writing a C code for that algorithm is very simple. So you should know how to create an architecture for a given problem. And on the maybe tomorrow's lectures, I'll highlight that aspect more for a given problems, how you can create different architectures to meet the given specifications. That's a real challenge, and that's the most important stuff you should learn. What these languages are for. They're not for basic blocks, right? Now, this is another important thing which I wanted to highlight. Remember, whenever you want to call a block, the way I called here, first the output and then the input. If this looks very trivial, 3 inputs, 2 inputs, 1 output. If there are, let's say, 50 inputs and outputs, then chances are you can create some errors. A will go into B, B will go into C, something like that will happen. So it's better to follow this terminology by name. For instance, here, full adder, I'm calling some block full adder within this test bench. Now, what happens here is this C underscore out small lowercase is the output of the actual block. But in this, I'm calling that as capital capital C out. This bracket shows that this capital C out is connected to the small C out, or the actual output of the block. This is the block I have called in the test bench. One option is to put it like this, just sum here, C out here, A there, something like that. So sum means the first sum of that block will be the connected here. I don't know how to do it. This is error prone. This is ordered list. What I can do is I can put a name. I have three C out output, small sum output, small a, b and c are the inputs. This is nothing but a full adder. So I have three inputs a, b and c and two outputs sum and C out. So rather than connecting like this, where I have to follow a particular order, sum is first, so put sum here. Then C out is second. Then A. If I reverse it, there will be wrong connection. B will be connected to A will be connected to B. So this order must be strictly followed. It's highly error prone. Why not do it like this? This is much better. Why? Because you have C out. It means that the C out of the test bench is connected to the C out of the block under test. The sum of the test bench is connected to sum. So this is much better way of writing, of calling block which has large number of inputs and outputs compared to a traditional method. Use this. This is much more better compared to the traditional method, and this is much less error prone compared to this, because in this you have to follow the orders very strictly of the inputs and outputs. Now till now I zero delay simulation. How you can put delays? Look at this. Again same hash. Hash 5 A1 EAB. This is some block X. What does it mean? That is the AND operation, the output will be delayed by how much? 5 time units. Output will not be available at the same time and the inputs are changing. The output will be available after a delay of 5 time units. It's realistic simulation. Similarly, OR gate, the output will be available after 4 time units from t is equal to 0, because both are concurrent statement. It's not that the second statement will wait for the first statement. It doesn't really happen like that, because I'm putting them directly inside the module. They are concurrent statements. Both are concurrent. So the output out will not change at time t is equal to 0. The output out will change at time t is equal to 4. Similarly, the output E will change at time t is equal to 5. It will not change at time t is equal to 0. It is not zero delay. So if you want to be you have to be very careful. During functional simulation, you have an option. Be in the ideal world. Assume zero delay simulation. Don't put delays. But the biggest problem is results after synthesis will not match the results prior to synthesis. Because after synthesis, you will get delays. Prior to synthesis, you assume there is no delay. So the results will not match. This is very, very important. You have to introduce some delay at the functional level, maybe unit delay, so that the result should match before and after synthesis. This is a very important point. That's why I like it. So you can put delays in the data flow. You can put delays in the always. Learn those things. You must know how to write code with delays and verify at the functional level before synthesis so that the results matches. Is that clear? This is the message. The syntax you can learn. Of course, there are so many operators, I don't want to go through it. So many operators. I'll learn through examples. I don't want to teach you syntax. It is so boring. And it will not lead to anything. That you can build up by writing more and more code. The second block, which is a bit tougher than the first one, but you all know it, is an adder. Adder is the most important block. And why it's most important? Because the multiplier depends on the adder. The divider depends on the adder. And therefore, it is the most important block. Right? All the MAG operations. It's all MAG. DSP video is all MAG or something like that, accumulation. So, this is the data flow model of an adder. Slightly more complex problem. From the XNOR, I have moved to an adder, which is a slightly more complex problem. But look at this. This is the beauty of this Verilog or HDL. The power comes in here. Just look very simple. Module add data flow. What I'm doing? Assign. This is your concatenation. What does it mean? I'll add A, B, and C in. The LSB will be sum and the MSB will be C out. I've clubbed the two. The output will be 2-bit for the addition. Now the real power comes in here. The same code is valid for n-bit adder as well. I don't modify the code. Just what I have to do, I have changed these scalars to C out will be 1-bit, C in will be 1-bit, but A can be n-bit, B can be n-bit, and sum can be how many bits of the sum? How many bits of the sum? If I want to add two n-bit numbers, the result can be how many bits? Huh? If I want to add two 2-bit numbers, what can be the maximum? How many bits for sum? Think about it. If I multiply two n-bit numbers, how's the sum? So you must know, because you are now an HDL designer, so you must decide the word lengths. Word lengths are very, very important. If you are multiplying two numbers, what should be the word length that you have to choose? If you are adding two numbers, what's the word length? If you are dividing two numbers, what's the word length? Word length is very, very important. You have to meet the specification with the minimum word length, because word length decides the area. You have to keep the word length minimum, and there's no need. If I have 10 stages, all stages will have the same word length. If the data builds up, the initial stage must have shorter word lengths. As the data picks up, the next stages can have longer word length. It all depends how the data is varying. So you can have progressive word length rather than a standard word. It's very, very important. That's why I'm highlighting it. Word length is very important and must be rigorously chosen.